Hello, I'm Thomas Strasser from the Austrian Institute of Technology, and it's my pleasure to welcome you to the third part of the design and documentation of complex test system setups, the MOOC module 5. In this third part, we look at related approaches and concepts beside the approaches and tools that have been introduced in the first and the second part of this MOOC module. The structure of this part 3 is the following. We look first a bit on where we come from modeling side to the implementation side, and then I want to show you 4 different selected approaches which are related to the design and testing of complex systems. All of them are coming mainly from the energy sector. First of all, I want to show you here that in this slide, the different concepts and methodologies exist that tackles different topics from the technical implementation, where we mainly look at the realization of programs, for example, in different programming languages that you can see here, or also in a simulation setup with the functional mockup interface. For the interaction between different tools, we typically have different interfacing and synchronization approaches, like the functional mockup interface and the high-level architecture. For the synthetic description of the for the modeling and interaction, we typically use here more formalized approaches like XML. We have also semantic models and for the description of the interactions that you can see here, IEC, business application interoperability profile, and some others. On the conceptual side, typically we tackle generic structures and meta modeling, and the HDD that has been already introduced in the first part of this module can be located here on the conceptual and semantic part. On the right-hand side, you see from the energy domain different very well-known approaches, like the use case methodology according to IEC 62559, the IEC 61850 interoperability approach that also introduces semantic and data models for substations and distributed energy resources. Then we have the CIM, the Common Information Model, for describing the whole power system, kind of a domain ontology, and also the smart grid architecture model that acts more on the conceptual and semantic side. First of all, I want to show you or introduce you to the smart grid architecture model that has different origins, which I will start with. One is the NIST Smart Grid Framework. This framework has been developed by the National Institute of Standards and Technology, and it introduces 7 different domains in the energy sector, in the power system field, which tackles the bulk generation, the transmission and the distribution of electricity, as well as the consumer side. Besides that, we need also the operations in order to keep the whole system running, the energy markets and the service providers. They are on the one hand side connected, especially here on the bottom side, the electricity system shows also the electrical flow between these different domains. And we have also we need secure communication flows between all the 7 domains, which are also outlined here. This model has been slightly improved or extended on the European side through a smart grid standardization mandate. Here, mainly the distributed energy resources being introduced as their own domain, which are not shown here in the NIST framework. It's covered by the customer side, but here in the European extension, we have here this distributed energy resources explicitly mentioned here as domain. The transmission and the distribution form mainly the pan-European energy exchange system. If we look at the distributed energy resources, the consumer side and the parts of the distribution side, then we have typically the area of microgrids, which are also reflected here in the European model. A further model in the context of the development of smart grid is the automation pyramid. That's also very important. It shows the hierarchical structure of a typical automation system that starts with the sensors and actuators that links to the underlying machine or process. We have on the top layer side the programmable logic controllers that implement the control logic, and the supervisory side where we have the SCADA system, this supervisory control and data acquisition systems, distributed control systems, and human machine interaction approaches. Here we talk about visualization on the one hand side, but also supervisory control. And the top two levels are related to the planning, manufacturing execution systems typically are related to the planning of the different machines and resources in the shop floor. So there's look mainly at scheduling approaches, and on the enterprise level we have also the whole billing, controlling, and all the stuff are also integrated. Besides that, the grid-wise architecture framework was also part of the considerations for the SCAM. That typically looks at the interoperability of systems. Here two systems are shown, and there are different levels in the grid-wise architectures framework. There are 8 levels of interoperability, starting from basic connectivity over a syntactic and semantic understanding of the information that need to be exchanged up to the business context. And in the context of the smart grid architecture model, these 8 layers have been integrated into 5, as you can see here. In component, communication, information, functional, and business layer. And if we put everything together, so the NIST, or the European extension of the NIST framework, the automation pyramid, and the grid-wise architecture stack, then we're coming to the so-called smart grid architecture model. Here on the bottom, here we show only the component layer according to this simplified grid-wise architecture interoperability layers. The domains are formed by the areas domains of this extended NIST model. The zones, we have 6, besides these 5 domains, we have the 6 zones from the process to the market. They have been borrowed from the automation pyramid. Where we have on the higher levels the information management. On the process layer we have mainly the power system, equipment, and energy conversion system. When we put on top of this component layer all the other layers, then we come to the so-called smart grid architecture model. This is represented typically as a cube with these 3 axes: the domains, the zones, and the interoperability layers. So the smart grid architecture models, the SCAM, supports the specification of different smart grid applications, and it mainly addresses interoperability between these different domains, zones, and the interoperability layers. It provides a structured process linking use cases into system architectures, and it introduces these 5 main interoperability layers, the 5 domains and the 6 zones. Typically, when we talk about or try to link use cases to the SCAM, then we typically follow this kind of information flow. We start typically with a use case description, as it's shown here. There are different ways to describe use cases. UML, Unified Modeling Language concepts can be used here. We have also the IEC 62559 use case approach standard, which introduces corresponding templates for the modeling or description of use cases. Then, as next, we typically design or describe the business layer, or analyze the business layer, then afterwards the functional layer, and the followed by the component layer, and as a final steps, the information in the communication layer being analyzed. I want to show this approach, or this structure, this workflow in the following few slides in form of different examples. So the business layer, here we look mainly at economic and regulatory constraints, business processes, business objectives. In the bottom you see here the component layer represented where a distribution grid is shown here with a distributed generator. We have here on the in the different zones the controllers, the intelligent electronic devices, data collectors, data concentrators on the operation side, the distribution management systems, visualization in the control center, and then later on also customer relationship management software. So on the business layer, all these interactions are being usually described. Broken then down in a functional structure. Here, here this example, there is a voltage control, volt-var control approach shown, where we need on the one hand side the data acquisition from the distribution grid and the generator, the distributed generator on the one hand side. Then in this SCADA system, all this information are being collected. The volt-var control approach is here executed centrally and sends then control signals to the distributed generator. So this is typically the view on the functional layer, breaking down a voltage control application to the functional layer. As a next layer, we look at the component layer, which we have already briefly seen, but here it says specifically outlined with the power system itself and the power system components, the transformers, the generator, the distributed generator in this side. In this example, the low voltage bus bar or feeder, very simplified represented, the medium voltage grid and the connection to the high voltage grid. We have this DR controller, the distributed energy resource controller, the distribution IDs and so on, the data collectors and the computing system, the upstream level supervisory control and business process computers. And all of them need to communicate, so therefore it's important to specify the communication at the information layer. On the information layer, mainly the data models are being described. In this case, we use ISC 61850, 7.4 for the IEDs and 7.420 for the DR controller. And we have for the more grid-related description, the SIM for the distribution SIM. That's the information side, and the communication side shows here the explicitly used communication protocols that can be mapped in order to represent this use case and the whole architecture in this smart grid architecture model. This model has been also adopted to other domains. In industry side, the reference architecture model for Industry 4.0 has been introduced, the RAMI 4.0, so it borrows a lot of concepts from the SCAM, and the RAMI 4.0 nowadays replaces more and more the originally introduced automation pyramid. In the automotive sector, there's this automotive reference architecture model, the ARM. In the marine, we have the MAF, or in the city, the CG-CAM, GS-CAM for the generic smart city architecture model. So you have seen that this kind of architecture model can not only be used in the energy sector, it can be also transferred to other sectors, as it outlined here. Further concept for the documentation and the description of testing approach or testing needs is this further approach is the SMILES precise approach. SMILES was also a European project where this precise approach has been developed, and it's an approach for the preparing concise information for simulation experiments, where you describe a test system and the testing needs for a simulation study that can be then mapped to different tool chains, as it here outlined, for example, to DTU ones or AIT ones. It facilitates cooperation among experts using different modeling paradigms and also different modeling tools. It enables a workflow that combines different tool chains and create added value by unlocking the synergies. It's based on the IRIGRID holistic testing description approach, and it provides adopted HDD templates. To compare it with the HDD approach, it tackles the test case description, so where it describes the system under test, the use cases, the test criteria, and the general test case. Plus, it adds test design, general simulation setups, and test specifications. The specifications are a bit comparable with the test specifications from the HDD approach, but it doesn't tackle the experimentation part, so of the original HDD. Here you can see also very briefly the different covered aspects of simulation experiments, the test application, where we have the use cases, test cases, and test specification. Then the reference descriptions, system configurations, which control functions are used, input data, and then modeling and optimization, which components models are being used, the related key performance indicator that's linked to such a simulation study, and the different objectives functions. As you can see here, this part is based on IRIGRID, the HDD, the test applications, and here the HDD was also used for the reference description and the modeling and optimization, but here in the precise approach, extensions have been made especially for simulation experiments. So to summarize, the precise approach is a kind of an adoption of the HDD approach, mainly for simulation-based experiments. A further approach that I wanted to introduce was developed by the Electra Integrated Research Program. It's also kind of a validation approach that tackles the testing, the description and design of testing setups. It is a three-stage approach that is based on SCAM. Typically, the first stage looks at the different smart grid solution descriptions. It focuses on control because Electro had a strong focus on control approach, the so-called web of cell approach, where different control concepts have been introduced. Then afterwards followed by a SCAM function information layer mapping. Then in the section stage, so the stage 1 consolidates functional descriptions. The stage 2 looks at laboratory implementation descriptions. So on the one hand side, the laboratory infrastructure comes into place and also reference power system. And in this third stage, you have the experimentation descriptions and the KPIs to map the SCAM description to a specific laboratory setting. Then you have the test execution, the test cases, and the KPI extraction. I want to show you this approach in form of an example. We start here typically with the use case description in IEC 62559, this IntelliGrid use case approach, followed by the SCAM functions and information layers per use case. So we have here taken an example from the Electra web of cell concept, where a restoration control approach is being described with the different elements in the distribution tier and customer domain over the different zone, where the different functions are being described here. Then in the next steps, we look at the very generally in the first stage, we look which reference power system is being used. For example, the UK power system is used. Here in this case, it was divided into different control related cells, 7 cells, following this Electra web of cell control approach. And then we look how such a description, such kind of an experiment can be realized in a lab focus, in a lab context. And as you can see here, the different elements are mapped to different PCs, to different IADs. here's mainly a simulation-based approach is described on the left-hand side. On the right-hand side, you see also the physical cells, which have been emulated in a laboratory context with different power sources. You see here is this as the general on the generation side, then the distribution cabinets and some load banks. So we have here the cells 1 to 3 have been realized as physical cells, whereas the cells 4 to 7 have been implemented in a real-time digital simulator, where also related generation models, transmission, distribution lines, and transformer models and load models have been implemented that are working together with the physical cells. And then this is the description of the laboratory setup in the second stage. And then in the third stage, we have the experimentation plan and the KPIs that look at the different key performance indicators and how the experiments have to be carried out in this setting. It has a lot of very commonalities with the HDD approach, but it have been developed independently, especially before the HDD came out. And last but not least, I want to show you also a very focused approach for testing that's mainly on the interoperability testing side. The key challenge here is that we need a convergence or we have a convergence of industrial sectors with different standards, cultures, and technical background. We have typically multi-vendor devices and components, and they should able to work together. And if we look at the definition from the Smart Grid Coordination Group, this is a subgroup of the SENS and ELEC-ETSI approach, and they define the interoperability as the ability of two or more networks, systems, devices, applications, or components to interwork, to exchange and use information to perform required functions. That is typically often modeled with the Smart Grid reference architecture model, where we have the interoperability across these 5 layers that are introduced a couple of minutes ago. But the big question is also how we can test such a specific architecture in different applications. And here we have on the one hand side the SCAM that helps us in order to identify interoperability needs. So we have interoperability of various building blocks are necessary. We have the we need to look how the different components and parts need to work together. This is typically being modeled in the SCAM, but the big question is also how to validate and test such a description. And there we have at least 2 different approaches. One was introduced by the European Commission, especially by the Joint Research Center. They have made a proposal for interoperability, for an interoperability testing methodology that uses also design of experiments methodology for the test planning. And another one comes from the Smart Grid Austria, the so-called IS project, and they have developed also guidelines and software tools for interoperability testing, and they took a very interesting path because they took an approach that is very common nowadays in the healthcare sector. But first I want to show you very briefly the approach from the JRC. On the left-hand side, you typically see the interoperability process, where you look at the functional analysis, the selection of use cases, then you map different or suitable standards and technical specifications to it. Then you typically do a profiling, you select the specifications, you create basic application profiles, and for the testing you extend them with interoperability needs. They are called basic application interoperability profiles. So this is typically the process, and GSE has developed the methodology. That starts with the use case creation. We have the stakeholder needs and other use cases that are followed by the on this generic interoperability process on the left-hand side with the business application process creation. They have developed specific tools for it. Then in the next step, they map the different interoperability requirements to it, coming out with a basic application interoperability profile. And that is then being used in order to realize a test. They start typically with a design of experiment, a statistical design of experiment, a so-called DOE approach, where the experiment is being based on statistical information being planned. Then the corresponding tests are being executed that you can see here. The equipment under test in a test bed with the different test cases, and then the test cases tests being executed and the results are being analyzed. And in case the outcome is not good enough, then the tests are being refined and re-executed. So this is one specific approach. It has it looks from, at least from the meta level, from the stages, has comparable stages to the HT approach. Another one, especially for interoperability testing, has been introduced by the Austrian IES project, integrating the energy systems. Also, they start typically with use cases and profiles in the SCAM framework. And the main approach here is to define a technical framework for a specific application that need to be tested. For example, here I've shown a virtual power plant. And the technical framework consists of two volumes. Volume 1 looks more on the business objectives, the business overview, and the business functions, whereas the volume 2 work looks on the technical, more on the technical side, with the integration profiles, business application, basic application, and basic interoperability, basic application interoperability profiles. And looks at the transactions, communication procedures, and the actors software modules that is being documented in this technical framework. And this technical framework is then used in so-called connectathon events where the vendors meet together and following these technical descriptions for the interoperability testing, doing the interoperability testing in this connectathon. And the results are being then documented. They have also specific software tools in order to define the technical framework and to plan the different tests and to analyze them, the results in the end, and document them. Here you see a bit more in detail the testing workflow of this IES approach. So you have typically this cooperative workflow where users, purchasers, and vendors, developers participate. They define the use cases and the integration profiles, define use cases, specify the profiles, and derive the technical frameworks. And then in these connectathon events, they typically test interoperability according to these profiles, also to conformance testing supported by specific software tools for the planning, the test execution, and the test documentation. And then the connectathon results are being analyzed and documented. We have a registry of interoperability products as a final results in order to ensure that the different developments from the vendors, developers are interoperable to satisfy the user needs. So that brings me to the end of this part 3 of module 5. With a short summary, I have shown you the so-called smart grid architecture model, which is a structured framework for smart grid design. It defines layers, domains, and zones to support interoperability and also look at system architecture development. adaptation of the aero-grade HDD was done by the in the SMICE project with the precise approach, which enhances simulation experiment documentation. It supports the collaboration across tools and tool chains and extends the aero-grade HDD methodology. Then I have shown you the electro-IRP approach, especially the testing part, which looks at, well, also based on an SGAM based validation approach in 3 stages, where it starts with functional descriptions, maps it to lab implementation, and then in the 3rd stage executes the experiments together with the linked KPIs. And last but not least, a very specific approach that mainly looks at interoperability and how interoperability is being validated, tested of implemented solutions in order to ensure that multi-vendor systems can interwork. I've shown you very briefly these 2 approaches from JRC, the Joint Research Center, as well as the integrating energy systems methodology for the planning and execution and documentation of interoperability testing approaches. I hope you have seen here or get more information with these 4 approaches that's somehow related to the can be compared to the HDD methodology, but tackle came from different development and tackle different application fields. Many thanks for your attendance.